Okay. Let's start the second talk today. So the second talk today will be delivered by Professor Serge Haroche with the title, How Blue Sky Science and Technology Nurture Each Other, Example of Quantum Physics. Professor Serge Haroche is Professor Emeritus at the College de France. He is a member of the French Academy of Sciences and a foreign member of the National Academy of Sciences, USA, and he was awarded the Nobel Prize in Physics with Professor David Windenland in 2012. So CTU is very honored to have Professor Haroche as the chairman of the IAS starting from 1st March 2018. And this is his first visit to CTU since he took up the appointment as IAS chairman. May I now invite Professor Haroche to the stage. Professor Haroche, please.
Yes. Okay, can you hear me? Okay, so it's a great pleasure for me to be here to give a lecture in this conference, which is honoring the French-Hong Kong collaboration in science and the 80th birthday of Philippe Ciarlet. I have been invited by Philippe for the first time here in Hong Kong 3 years ago in 2015, and since then I have come every year enjoying the very stimulating atmosphere of Hong Kong and the friendship of Philippe, and I have been able to visit people here and also to organize last year a very interesting workshop on quantum technologies, and I hope that I will have the possibility in the future to organize other interesting workshops and conferences. So congratulations, and I'm sure we'll continue for many years to come to collaborate with, to work here and to collaborate with the French Academy and the College de France. So I have decided to give a very general talk because I know that you are not all physicists here, so I will try to give a talk discussing, by taking examples in physics, the connection between blue sky, that is basic science, and technology and applied sciences. And I'm sure that we all agree that there is a very deep connection between the two, but it's not always agreed by everyone, and I think even if you agree, the examples I will give you here might give you ammunitions when you need to convince politicians or some people that this connection is very important. When you ask a question about why are we doing scientific research, there are two types of answers. The first one is to say that we want to satisfy our curiosity. It's called curiosity-driven research or blue sky research. It is basic science. We just do things to understand nature. And there is another answer, which is, of course, the usefulness of science. We do that because we want to achieve, to get results, to build, to have new devices which will help us to live better. And this is what politicians are very interested in, and when they develop programs for science, they very often talk about societal needs. We want to do things which will be useful, and this is applied research. And policymakers often favor, of course, this because they want to have fast results, and they very often consider long-term curiosity as a luxury. And what I would like to discuss here to illustrate is the fact that the history of science tells us that it's a mistake to distinguish between the two. Blue sky research and technology nurture each other all the time. They are in symbiosis with each other. And blue sky research is necessary to do technology, and on the other hand, technology, of course, helps basic science by allowing us to probe deeper into nature. So I would like to illustrate that, and I've just, on this slide, give a very broad overview of the big progress of blue sky curiosity-driven research since the 17th century. very deep questions about the nature of light and matter have been asked starting from the 16th or 17th century. What is light? Is light a wave or an ensemble of particles? At which speed does light propagate? People like Newton, Huygens in the 17th century have opposed each other on this topic. In the 19th century, Fresnel has demonstrated by quantum interference experiments that light is a wave, and Fizeau in the mid of the century made the first precise measurement of the velocity of light. At the same time, fundamental questions are also asked about the nature of matter, what it is made of, and what are the properties of electricity and magnetism, which of course occur inside matter. And physicists like Coulomb, Faraday, Ampère, and culminating with Maxwell have asked this question: what is matter and how does matter interact with light? And this has led, of course, to the great discovery at the end of the 19th century, the electromagnetic theory. Electric and magnetic fields propagate in space according to Maxwell's equation, and the atomic theories that matter is made of particles called atoms. These atoms carry magnetic moments, and they interact with light according to the laws which have been discovered later. Light and matter obeys, in fact, strange laws with counterintuitive properties. Light, which according to Maxwell was a wave, has also a particle-like character made of photons, and atoms, which are considered to be classically as particles, have also a wave-like character. This is quantum physics, and quantum physics and relativity have come at the end of the 19th, beginning of the 20th century from the work of great physicists like Planck, Einstein, and Bohr. So this is a very fast and very superficial overview, but I want to just stress that the scientists who made these great discoveries have no application in mind. They just wanted to understand nature, and yet they have led to innovations which have changed completely our way of communicating, of producing energy, of storing information, of making medical diagnosis, and so on. And all this has come from the basic science, which was on the previous slide, and it has come very often in a very unexpected way, from the combination of breakthroughs coming from different aspects of fundamental physics. And I would like to look at a few examples. And I will start again from Maxwell's equation, because I think Maxwell's equations are a kind of towering example of the beauty of basic science. In fact, what Maxwell did was to start from the results, the experimental observations of Faraday and Ampère, and he found out that the electric field produced by electric charges and the magnetic fields produced by electric currents, which were studied by Coulomb and Ampère and Faraday, influenced each other. The variation of an electric field produced a magnetic field, which in turn produced an electric field, the two propagating through space, making up waves. Here the blue and red vectors correspond to electric and magnetic fields. These waves are characterized by wavelengths, which is the distance between two crests of the field, and by frequency, which is the rate at which the field evolves in time. And Maxwell was able to write the equations, which I will not write on this board, which describes the evolution of these electric and magnetic fields. And I will just show you one equation in this talk, which is this equation. He was able, from Maxwell's equation, to derive the velocity of this electromagnetic field, which is 1 over the square root of the product of two constants, epsilon, which is the electrostatic constant, the constant which intervenes to compute the forces between two electric charges according to Coulomb's law, and mu, which is the constant introduced by Ampère to describe the force between two currents. And epsilon and mu being known, Maxwell computed C, and he found the value that Fizeau had just measured about 10 years before for the velocity of light. At that time, nobody knew that light was an electromagnetic field, and so Maxwell immediately understood that it could not be a coincidence. And I just show you here the page, the manuscript, which is conserved at the Royal Society in London, in which Maxwell described this great discovery. He compares the two values of the velocity of light 298 millions of meter per second and 308 million meter per second, which are the value coming from Fizeau experiment and from his calculation. And he said that can be a coincidence, and if you read the last 3 lines, I don't know if you can read them well, so I have written them here. The agreement of the result seems to show that light and magnetism are affections of the same substance, and that light is an electromagnetic disturbance propagated through the field according to electromagnetic laws. I think this may be the most important sentence in physics and in science, maybe in general, because it combines, it unifies electricity, magnetism, and optics in a single sentence. Another thing I would like to stress here is that Maxwell would not have liked the Brexit. Maxwell used the metric units here. It does not give the velocity in miles per hour, but in meters per second. And in fact, it's not a joke. Maxwell was the father of the international system of units, and this is very important today because I think in a couple of days in Versailles, there will be a meeting to redefine the units, and Maxwell played an essential role for that. He said already in the 19th century that time could be measured as the frequency of vibration in atoms, which is exactly the way it is done now, and that one could measure also length from time using the velocity of light. So he had already a visionary premonition of what would come later on. So this, what I want to say also is that the visible light is also only a very small window in the spectrum of electromagnetic radiation, and what Maxwell's equation predicted is that at longer wavelengths and shorter wavelengths there was some invisible light, and this is the beauty of theories. A theory should explain what has been observed, but also predict new things to happen. And of course, a few years later, Hertz discovered the radio waves, long wavelength radiation, and then Röntgen discovered the short wavelength radiation, X-rays. And in fact, Röntgen received the first Nobel Prize in Physics for that, and he is the first of a long line of physicists which I will talk about in the remaining of this talk. So of course, this short and long wavelength radiation had a fantastic importance in technology. The long wavelength radiation was the one which was used for telecommunication, for radio and television and cell phones and so on. And there are also the long wavelength radiation which we receive from the universe in the cosmic radiation background, not to talk about microwave ovens. And the short X-rays are important not only for medical diagnosis, but for all kinds of diagnosis of matter at the microscopic level. So you see here already a connection between blue sky and applications, but it goes the other way. By trying to understand deeper how long and short wavelengths is interacted with light, physicists have understood that classical Maxwell's equation, classical physics was not enough, and this new question led to relativity and quantum physics. So at the turn of last century, beginning of the 20th century, there was a big revolution, not only in technology, but in concepts. And I just want to recall here what people were thinking in the year 1900. This is a picture of Lord Kelvin, who was the Pope of classical physics. And what I want to show you here is that the modern technologies which have become very common in the 20th century were impossible to imagine by pre-quantum age physicists. In the year 1900, there was a big world fair in Paris. And at that time, there was a big hope in the progress of humanities. And people were trying to figure out what would be the world in the year 2000. And a lot of postcards were published. And I just show you a few of these postcards. This was supposed to be the world today. So you see that it's a very, very naive, you see en l'an 2000, and this is German visions of the year 2002. So they were absolutely unable to predict what happened. The example of quantum technologies which were not anticipated in 1900, you have the computers, of course, which are made of transistors in which the electrons behave in ways that only quantum physics allow us to understand. The laser, which cannot be understood if you don't know how atoms interact with light at the microscopic level. You have atomic clocks and the GPS, which are also coming from quantum physics. Finally, you have nuclear magnetic resonance, magnetic medical imaging, and this is, of course, just a few examples. And if you just let the computers aside for a moment, the three inventions that I show you here had their origin in one blue sky experiment that I want to talk to you about now. And I want to show in the rest of the talk how, starting from a very simple experiment which was motivated by curiosity, all these applications in different fields came quite by chance, or maybe not by chance, but by the convergence of various discoveries. So everything started in 1922 when Otto Stern in Hamburg tried to understand the nature of magnetism. He used a setup which is shown here. You have an oven which was full of silver, and silver was evaporated in vacuum, made an atomic beam of silver atoms propagating through space, and these atoms were received here just on a glass plate. And the atom deposited on the glass plate and made a small spot. And the atoms were propagating in between the poles of a very strong magnet, which has a gradient of magnetic field. And the idea of Stern was that if atoms carry magnets, these magnets would be deflected by the force of the magnetic field, and by looking at the spot on the screen, one would have the distribution of magnetic moments which will be measured. And classically, what he expected is to find a kind of diffuse spot because the magnetic moment could take any value. And he was very surprised to find, in fact, two discrete spots. This is an example of what is called spatial quantization, which shows that the magnetic moment can be only either up or down, but cannot have just any kind of orientation. And this was a very famous experiment. The magnetic moment is quantized. In fact, what was found later on that he was measuring here the magnetic moment of the electrons in the silver atom. And this setup separates the magnetic moments, which are called spins, pointing up and down. And I will show you here the trace, the original trace observed by Stern. You see here at the center, you have these two spots which are well separated, and they converge on the edge because the gradient of the magnetic field decreases at the right, at the left. So it's a very, very crude experiment, much less sophisticated than what we do now, just receiving atoms on a plate. But I claim that this simple split trace is heralding the quantum revolution in technology. And the next step was how, and Otto Stern received in 1944, the year of my birth, the Nobel Prize in Physics for this work. In fact, he was a Jewish German who emigrated to the United States and who ended up his career in, I think, in New York. But in fact, Otto Stern had a postdoc visiting him at the beginning of the 1920s. Isidor Rabi was also a Jewish guy from Eastern Europe who had emigrated to the United States, made his PhD in the United States, and came back to Germany as a postdoc. It was a time when the flux of postdocs were going in the opposite direction as it is today. And he learned the technique of molecular beams, atomic beams with Stern, came back to New York, settled in Columbia, and started to use the method to measure the nuclear moments, not of electrons, but of nuclei. And his setup was a variant of the Stern experiment. Now we have two zones, A and B, in which the gradients take opposite directions, which means that the magnetic moment will undergo a kind of S-shaped trajectory when crossing the two zones, and it will be focused on a detector. This detector was a little bit more sophisticated than the glass plate of Stern. It was a hot wire. When the molecule of the atom just collided with this wire, they lost an electron, and it gave rise to an electric current. And this electric current was proportional to the flux of particles which arrived on the wire. Now, the big idea of Rabi was to add a third zone, C, in between A and B. In this zone, a cavity was applying a microwave field to the spins. And I just give you here a very simple picture. The spin up and down have slightly different energies. And this energy is matched by photons which have the right frequencies to make the spin flip from up to down. this is called magnetic resonance. And when the spins were flipping, it's clear that the spin which was otherwise would go along this S-shaped trajectory would miss the detector. And so at resonance, the signal on the hot wire should decrease. And what was observed is this kind of curve with a signal which decreases when the frequency of the microwave is exactly the one which corresponds to the transition between the two states. And by measuring this frequency, Rabi was able to measure the magnetic, knowing the magnetic fields, to measure the magnetic moments of various nuclei, the protons, the deuterium, and others. And these experiments were done in the 1930s in Columbia. Rabi got the Nobel Prize for that, and these discoveries opened the way, as I will show you now, to the MRI, the atomic clocks, the GPS, the laser, and so on. So what happened next? In 1939, Rabi, at a conference, reported about his results, and I found on the internet a copy of the front page of the New York Post, dated December 1939. You see the headline, "We are all radio stations, Columbia scientists report. Everything, every living thing on Earth is a radio broadcasting and receiving set, unconsciously sending and receiving long wavelengths wireless radiation." So what Rabi had said, I think, is that the atoms that he had on his atomic beam were the same atoms that we have in our bodies. And since these atoms are emitting and absorbing radio waves, the atoms in our body should do the same. And one could use maybe this information to do something. I don't know exactly what he said, but this is what the journalist has recorded. And in fact, this is what happened, of course, much later. But it was, of course, the technology at the time of Rabi was not enough for that. One had to be able to observe this not on an atomic beam, but in condensed matter, in solid and liquids. And the next step was taken by these two gentlemen, Felix Bloch and Edward Purcell, one working in Stanford, the other in Harvard, who invented the nuclear magnetic resonance in solid and liquids. And their setup is shown here. So it's no longer an atomic beam. You have here a liquid or a solid sample. You apply a microwave through a frequency generator, which is connected to a coil here, which is an emitter coil. And when the spins flip, they produce a signal which is received by this coil acting as a receiving antenna. This is a receiver coil. And you have, of course, to put the sample in a large magnetic field. And when you change the frequency of the microwave, you can record resonances which are a signature of the species which are inside the system. And this is the basis of nuclear magnetic resonance. What I want to stress is that this was not possible before the war. It's a blue sky discovery which has been made possible by the technological advances, especially the research on the microwave sources which were used for the radars during World War II. So you see the kind of connection between basic science and applied science, and this has led to NMR probes in physics, in chemistry, and biology. But when Purcell was asked what would be the use of NMR, he said he did not know. And in fact, on the next slide, I just show you here the beginning of Purcell's Nobel lecture in 1952, because it's a beautiful, I think it's a beautiful example of the kind of wonder, exhilaration which scientists get when they make a blue sky discovery, because it connects things which are not seen, and it gives a feeling that you understand something mysterious in nature. So he said, Professor Bloch has told you how one can detect the precession of the magnetic nuclei in a drop of water. Commonplace as such experiments have become in our labs, I have not yet lost a feeling of wonder and of delight that this delicate motion should reside in all the ordinary things around us, revealing itself only to him who looks for it. So it's politically incorrect. Today we would say to him or her. I remember in the winter of our first experiment, just 7 years ago, looking on snow with new eyes. There the snow lay around my doorstep, great heaps of protons, quietly precessing in the Earth's magnetic field. To see the world for a moment as something rich and strange is a private reward of many a discovery. So this was just pure basic science. And it took something like another 20 or 30 years before it became a very famous application for MRI, magnetic resonance imaging. This is based on the fact that we have a lot of water molecules in our bodies. The hydrogen atom carries magnetic moment, which precesses in a magnetic field. You have to apply a very big magnetic field, so you have to put the bodies inside a coil made of superconducting wires, which have to be cooled at very low temperature, so that's why it's so impressive to be subjected to this kind of measurement. You have to apply a microwave, which is with frequencies proportional to the magnetic field, because this field produces splitting between the two levels, which is observed. And the very beautiful idea was to use a field which has a very strong gradient, so different points inside the body resonate at different frequencies, and so you can, in this way, get signals which tell you what is the density of protons everywhere. And of course, you need very powerful computers to transform this raw signal into images. And so this is what is now the MRI. And you see that at the time of Purcell, it was impossible to imagine because there were no computers and no high-field superconducting magnets. But of course, this has led to a fantastic method, not only for physicians, but also for researchers. You can study the static and dynamical behavior of the brain. If you start to think about something or to make a move with your hand, you produce an activity which increases the flux of blood at some part of the brain. Since the blood is carrying hemoglobin, which has a magnetic moment, it changes the signal. And this is called functional MRI, and it allows to explore the brain function and to study the emergence of consciousness. So this is very something which Purcell was unable to imagine, neither Bloch nor Purcell. And in fact, one of the big, great rewards of being a physicist is that you can meet these kind of people. When I was young, I met Bloch in Stanford and Purcell in Harvard, and it was really an experience. These were fantastic people. They could have got another Nobel Prize. Bloch is the one who understood how electrons propagate in metals, Bloch waves, and Purcell discovered was the founder of radioastronomy. He observed the microwave produced by hydrogen in space. So these were really fantastic people. So let me go now to another important point. I will here make a brief history of the measurement of time. If you want to measure time, you need to have a periodic phenomenon. For example, in the 14th century, in the tower clocks, you had a vertical, you had a kind of thread with a pole, and due to the torsion of when you just displaced this horizontal called foliot, it was starting to oscillate, and you needed an escape mechanism to count the periods, and this was the first clocks. Then in the 17th century, Galileo and Huygens perfected the system using the pendulum and again an escape mechanism just to count this time somewhat higher frequencies, a frequency of about 1 meter long pendulum. Then in the 18th century, the pendulum was replaced by a coil whose frequency was much higher. It was first chronometers, mechanical watches, and the marine chronometer developed by Hooke and Harrison to keep the time while the ship were traveling and to measure the longitude. And then in the 20th century, the oscillation went at a higher frequency. You measured the vibration of a quartz, of a small quartz made of two, you have here, a diapason of quartz diapason whose oscillation, a fork whose oscillations were transformed into electrical current by the piezoelectric effect, and this was the work of Curie at the turn of the 19th and 20th century. If you look at this evolution, 6 centuries, and look at the precision, the general principle is always the same. You take an oscillator which is called to an escape device which counts period, and you need to go to higher and higher frequency to increase the precision. So what was the precision? In the 14th century, it was 1 part in 100. You had to reset the clock every day because it was just shifting by about a quarter of an hour per day. Galileo's pendulum is a few, let's say, minutes per day, if you set it well. Then the marine chronometer was about a minute per month, or to a few seconds per month, which was what was required to keep the time for longitude measurement. And the quartz fork, it was about 1 second per year, which was supposed to be fantastic. Now look at what happened when atomic clocks were developed. The standard Cesian atomic clock has now 10^14, which is a second per millions of years, and the latest atomic clock, which use lasers, have now a uncertainty of 1 part in 10 to the 18. So you see that during the last 50 years, one has made on a logarithmic scale much better than the 6th century, which have preceded before the advent of atomic physics. And the microwave atomic clock operates on an improved Rabi machine. You see here, it's exactly the same machine as Stern and Rabi. Now the improvement is that microwave is applied at 2 different places. You have 2 microwave pulses. This is an idea that Norman Ramsey, who was a student of Rabi, developed in the 1950s. The oscillation of electrons in an atom is much faster and much more stable than that of a pendulum, a spring, or a quartz, which is demonstrated in the system. And you see by tuning the microwave, one observes now a signal which has fringes because of the fact that we have 2 zones instead of 1. This is a quantum interference effect. And the idea is to lock the microwave so that you stay at the top of the central fringe. And this is the principle of these atomic clocks. The uncertainty is for a standard clock of 1 part in 10 to the 14, 1 second over 10 million years. And these are the clocks which are used in the GPS system. Rabi got the Nobel Prize in 1999 for this kind of development. What is a GPS? You have an ensemble of clocks which are sent in satellites. These clocks are synchronized with each other at this level of precision, 1 nanosecond per day. And they send signals to the receivers, or to the cell phones that you use now for the GPS recording. And by triangulation, if you have 3 or 4 satellites, you can find your position on Earth with a precision of about 1 meter. What I want to add is that it's not only quantum physics, it's also special and general relativity, because you have to take into account the fact that the clocks which are the velocity with respect to yourself are different heights in the gravitational field, have different times. And the story says, I don't know if it's true, that the engineers who developed the first GPS system back in the 1970s did not put the relativity corrections. They thought that there was some esoteric effects for theoretical physicists, and their software was off by kilometers, and they had really to include these corrections. And so everyone which uses the GPS system to find the street, to find a position in a town, and to use the GPS in his car or her car, is demonstrating the usefulness of special and general relativity on a daily basis. So this is the second application. Now, what about the lasers? The laser is based on another blue sky effect, stimulated emission of light, which was discovered by Einstein in 1916. The idea is simple. Einstein wanted to find out the equilibrium between light and matter, the thermal equilibrium between light and matter, including the process which had been discovered by Niels Bohr in 1912, which is called spontaneous emission. What Bohr has discovered that if an atom is excited, if an electron is in upper state, the atom will fall back in the ground state by emitting a photon. This is called spontaneous emission, and this process is random. It occurs at a random time with a random direction for the photon to be emitted. What Einstein tried to use this process to understand how matter and light come into equilibrium, to find the famous Planck's law, and he found out that this was not enough. It has to add another process which he called stimulated emission. If a photon impinges on an excited atom, there is a high probability that another photon will be emitted, not randomly, but with exactly the same direction, the same phase, and the same frequency as the first one. In other words, one photon triggered the emission of a second identical photon. Light calls for light, And this is an amplification process. And this has led to the maser and then to the laser. And you know how a laser works. You need a cavity which keeps the photons, keeps the light going back and forth between the mirrors. The light passes over and over again on atoms which have to be excited, of course, by some process, electric discharge or a side lamp. And by amplification, you get more and more light. And if one of the mirrors is slightly transparent, the light is getting out, and this is a laser beam. And this laser light has properties which are very different from the one of a classical source. Whereas in a classical source, the atoms emit independently radiation which have random frequency, phase, and directions. In a laser, all the atoms emit in step with the same frequency, ideally the same frequency, the same phase, and the same direction. And this is what we call tamed light as opposed to the wide light of the sun of classical sources. And again, this started in the microwave domain with a Rabi machine. You see here, the first system was called a maser, microwave amplifier, but still made emission of radiation. And you see here a picture of Towns and Gordon with a Rabi machine at Columbia University, and the first maser operated with ammonia molecules. It's a variant of the Rabi machine which emits a current microwave at the frequency of the molecular transition. And the question, what is the use for this? And the use, there are many uses. It's again a Nobel Prize. Towns got the Nobel Prize in 1965 for this invention. And of course, all the uses came when it was extended in the optical domain. And the laser, of course, is a fantastic source of light. I just summarize on this slide some aspect of this light. It's intense, it's directive, it's monochromatic, it's coherent. You can focus it and achieve fusion and evaporation of matter, and you can reach the highest temperature that you can find in the inside of stars, millions of degrees by focusing laser beam. And on the other hand, if you use it properly, you can use lasers to cool matter and produce the coldest object in the universe, objects which are at the temperature of billions of a degree, nano, Kelvin, pico-kelvins. And at this temperature, you have new phases of matter, Bose-Einstein condensate, again, phases of matter which had been predicted by Einstein back in the 1920s. So this is one aspect of the physics you can do with that. Now, another aspect is a huge stability. You have ultra-stable light beams which oscillates without skipping a beat over millions of kilometers. You can reflect a light beam from the moon and compare the phase with the beam which started, and make interference experiments for that and measure distances with a huge precision. You can also obtain light pulses which extends over, by making many modes interfere, have light pulses which are as short as attoseconds, billions of a second, small bullets of light produced with lasers which allow you to probe matter at a very, very fast speed. So to summarize, it's a very flexible tool for fundamental research in physics, in chemistry and biology, and for a lot of applications. And just to conclude this talk, I will just briefly review 3 domains: manipulation of individual atomic systems for quantum information, ultra-precise atomic clocks, and gravitational wave detectors, which all came from the application of lasers in various fields. You can use lasers to control atoms one by one. You see here, this is a picture of experiments performed in the lab of Dave Wineland in Boulder. You see the 5 spots that you see here are 5 beryllium ions, which are held in a trap by a configuration of electrical and magnetic fields. Each of these atoms appears as a bright spot because it scatters the light of a laser, and it scatters the light of the laser only if it is in a well-defined energy level. If it goes in another level, this light disappears. And so you can use the laser light to control and to manipulate the atom between different energy levels. This was observed in 2000. Since then, you have had progresses. You see here 14 calcium ion, and here 30 calcium ion in the lab of Rainer Blatt in Innsbruck. Each of these ions is again scattering millions of photons per second into your eye, almost directly into your eye through a microscope. And each of these ions has two levels which are relevant for the experiment that you can call 0 or 1. And each ion behaves as a bit of information. It can store one bit of information. And in fact, it's a quantum bit because it can evolve into a superposition of 0 and 1 states. And two bits can be entangled with each other, can be put in a state such that you, to get information, you have to take into account that the two bits are correlated. Just to give you an idea, this chain of 30 ions has in fact 2 to the 30 quantum states, so about 1 billion states, and all the linear combination of this 1 billion states. So this is an abacus for kind of atomic abacus for quantum information. I don't have time to discuss that, but this is a basis for what we now call the quantum computer. We are very far from having an effective quantum computer, but this is a kind of toy object which allows us to understand what's going on in the system. So in Dave Winans and in the ion trapper labs, you manipulate matter with light. And what we did in Paris was the opposite. We trap light between mirrors and we send atoms one by one through the system, and we use this to manipulate the light beam, to manipulate the state of light inside the cavity. So just give you a very brief overview of what we do. One atom interacts with one or a few photons in the box. This box has very high quality mirrors, so the photons can stay in the cavity for about 1/10 of a second, and we send a flux of very special Rydberg atoms which are very sensitive to microwaves. So we again use lasers to prepare these atoms into the right state. The sequence of atoms crosses the cavity, couples with its field, and carries away information about the trapped light without absorbing the photons. So it's a kind of in vivo physics. We manipulate the field inside the cavity without destroying it. And we can control the number of photons, make it vary from 1 to 3 to 4 and so on. And we can store the information in the field. And again, it's something which is useful for quantum information, and I don't have time to discuss that in more detail. So this is one application of lasers. This is called cavity quantum electrodynamics, and it's a field which has seen a lot of progress during the last 20 years. Now, here we'll talk about the frequency comb synthesizer, which is a device which is an escape mechanism for atomic clocks at optical frequency. The idea is simple. In a laser, you can change the frequency of the laser by just changing the number of wavelengths between the mirrors. For each wavelength, you have a different mode of the electromagnetic field. And if you can have a mechanism which locks this mode in phase, what you will get is a sequence of pulses. At some time, all the modes will interfere positively, and this will give you a huge intensity. And then a little bit later, they will interfere destructively, and you have no light. And why is it important? It is important because if you get high intensity, you will have nonlinear effects, and you will be able to spread this phenomenon over wider and wider frequencies. You see what you have here is a picture of an optical fiber which has a kind of honeycomb nesting. And in this nonlinear structure, what you get is that if you have a few modes to start with, you generate by nonlinear effects other modes which are separated by the same kind of interval. And you see the kind of output that you get. If you look into a spectrometer, you have a wide spectrum from red to blue. In fact, you can cover 1 octave immediately. But if you look with a spectrometer with a high enough resolution, what you find is that this apparently white light is in fact structure made of a comb of frequencies which are separated by a fixed interval. And this is very useful because you see that if you count the modes here, you have a kind of ruler which span an octave and which allow you to count an optical frequency and bring this optical frequency back to a multiple of a microwave frequency that you can directly count. And this is the ideal escape mechanism which allows us now to relate directly the optical frequency, which is 10 to the 15 cycle per second, to a frequency that you can count. And the principle of the atomic clock, optical clock, is shown here. You start with a very stable laser. You use a beam splitter. Part of the laser beam is sent to an atom, hydrogen or strontium or ytterbium, an atom which has a very, very precise transition here. So you use this very stable laser, you adjust the frequency of the laser so that it exactly matches the energy difference in the atom. And the second part of the beam is sent to a frequency comb. You measure the frequency of the light in the other laser beam with an optical frequency comb. Or you can inversely lock the frequency comb to this very stable laser, and you can now count optical frequencies. And the laser comb locked to the optical atomic transition acts as a very precise clock escape mechanism. So you have two kinds of clocks which compete now. In one kind, you just have a single ion, aluminum or magnesium ion, and you lock the comb to this single ion. Or you can also use a collection of atoms, cold atoms, which are cooled by laser beams, and you can lock it to a frequency comb. I don't have time to describe the details, but just what I want to say is that now the uncertainty, which was 10 minus 14, becomes 10 minus 17 or 18, which makes clocks which are stable within 1 second in the age of the universe, or 1/10 of a second in the age of the universe. With this precision, if the clock is moving by 1 centimeter up and down in the Earth's magnetic field, you see the difference. So you see general relativity effects, and you can use that, for example, to map the inhomogeneity of density under the ground, and use that for geological application and for a lot of interesting application. So the last application, this is a stability in frequency. Now the stability in phase allows us now to measure small displacement with an outstanding precision. And this is the last example I give you here, how the gravitational waves were detected. You see here two Michelson interferometers, which two different locations in the United States. Now there is a third one in Pisa in Italy. And these Michelson interferometers operate according to the way I'm showing you here. You have very stable and intense laser, which is sent on a beam splitter, divided into two parts. One beam is going in this direction, the other beam here at right angle. The light is reflected on a mirror, it comes back on the beam splitter here, and it is adjusted in such a way that the light interferes destructively. When the light which comes back here, there is no light arriving here on this detector because of this phase opposition. Now, if a gravitational wave is falling on the system, it will slightly shorten this path and slightly lengthen this path. But when I say slightly, it's really slightly. The difference in path is 1/1000th of the size of a single atom. So if you look at our scale, you have to divide by about 1 billion or 10 billion to get the size of an atom. And then you divide by another billion, and you have the kind of effect that has to be detected. And you see the kind of signal here. When two black holes spiral around each other, in the end, they produce this kind of signal, which is observed on these detectors. So these billions of an atomic size is a result of a really cataclysmic event which occurred somewhere in the universe. You see, during this event, 5 solar masses have disappeared into this gravitational energy. 5 solar masses in 1 second. Compare this to the energy produced by our sun, which is 1/1000th of a solar mass in 5 billion years. So you see, I think, really awesome fact that you have this cataclysmic event, which you cannot even imagine, which has produced such a tiny effect, which has been detected on Earth, and this is blue sky science. And it has opened a new window to the universe. We now detect these gravitational waves, and it produces information about events, collapse of neutron stars, collapses of black holes, and so on, which will provide a lot of important information about cosmology. So I will conclude by trying to make a connection between blue sky research and innovation here. Everything starts by the observation of nature. Then it leads to theoretical models, for instance, quantum physics. Theoretical models make prediction of new effects, for example, stimulated emission, and this gives novel technology like lasers. And then the lasers can be used for more precise observation of the universe, and again give us a lot of tools which have revolutionized the various fields. And I call this a virtuous loop, the loop between basic science and applications, coming back from basic science to application, and application allowing us to probe basic science with more precision. So what will happen in the future? It's hard to make predictions, but think about the 1900 postcards. I think we have to be very careful to try to find out what will be the application in the 2100 years. But everyone is talking about the southern quantum revolution in technology. Will it be quantum computers, quantum communication networks, quantum meters, even more precise quantum clocks, or something else quite different? I don't know. We can only guess, but we know one thing for sure. If you don't go on with basic research, novel technology cannot be invented, and I hope that I have convinced you or reinforced in you the feeling that wonderful applications often emerge in a very unexpected way from blue sky research. And I will stop here and thank you for your attention.
Thank you, Professor Haroche, for this inspiring talk. So let's start the Q&A session before the coffee break. Yeah, Professor Lançon. Yeah.
Well, it's not a question, it's just a piece of a comment. Sorry, does it work? I will quote by, my memory is maybe not too true, but remember that when Charles Stones presented the maser in 1954, I think that somebody, a very high body, some kind of a president, said that it was a wonderful application without any possible, wonderful invention without any possible application.
Yeah.
That's just a comment.
It was, yes, it was an answer to a question which was not asked. But I remember I started my own career in physics about 10 years later, in the 1960s, and then the first lasers were already around. And we understood that they will be used for many interesting things, but we did not know exactly what. I was doing optical pumping experiment with classical lamps, and it was clear that the laser would improve that tremendously. And then someone published in 1968 a paper saying that lasers could be used just to change the position of atoms, to move atoms, and to cool atoms. This was a paper written by Arthur Ashkin. Arthur Ashkin got the Nobel Prize in Physics this year, in October. He is 96 years old, but he had this idea back in the 1960s that the laser could be used for that, but nobody had understood at that time that the laser could be made useful for atomic clocks, for instance, and the precision of the clocks now is absolutely unbelievable. And all these applications have emerged during the last half century, making tremendous progresses in all kinds of directions. I had the feeling that optics and atomic physics was undergoing a revolution. That's why I stayed in this field. And I remember a lot of my young friends and students at that time said, "Why are you going in the field of optics? Everything is known in optics. Spectroscopy is boring." And that was to some extent true, but the lasers have changed that, and this was not expected.
Okay. Other question and comments? Yeah, please.
Good afternoon. Thank you for the wonderful lecture, Professor. I'm not a physicist, so I just curious about how close we are to the theory of everything, the theory that bridge the
Yes.
quantum theory and the relativity. Thank you.
I don't know. I think, but you are right that there is a gap. Einstein was at the start of two theories which have really revolutionized our understanding of the world: quantum theory and general relativity. And it is true that these two theories are still at odds with each other. There is no quantum physics cannot, up to now, account for general relativity. And so there is something which remains to be discovered. And there are some ideas. People working in what is called string theory have been announcing for the last 30 years that the two would be merged. The problem is that string theory deals with phenomena at a scale, energy and distance scale, which are very, very difficult, maybe impossible to check directly. You need accelerators which are more and more powerful to observe things at a smaller and smaller scale. And the prediction of string theory cannot be tested up to now directly. But there are some ideas that maybe some new particles will emerge which even if we cannot observe them directly, will have effects which could be measured with high precision measurements. And maybe one day, certainly one day, things will happen. We are maybe in a situation which is a little bit similar to what was going on at the beginning of the 20th century. At that time, there was a hypothetical medium called the ether, which was supposed to propagate electromagnetic waves, and then the ether has completely collapsed and disappeared from physics. Now we are talking about dark energy, dark matter, which is unknown. So whether this will materialize or disappear because a new theory will be able to explain what happens without these concepts is something which remains to be seen. But there is a strong belief that there are particles beyond the ones that we know in the standard model, which are here somewhere in the universe. That's rather humbling because the particles that we know seems to represent only 5%. So I think this is the ultimate situation in which we here on Earth stop being the center of the universe. In the 16th century, the Earth was supposed to be the center, and then Copernic and Galileo came. We are not at the center of the universe. The sun is not, it's just a small star in the galaxy. The galaxy is just one galaxy, billions of galaxies. And even all these galaxies represent only 5% of what we know. So it's something which remains to be seen, and it's why physics and why basic science is so exciting, because we keep learning and we keep making great discoveries. But I don't know when this will happen. That's open.
Yeah, please.
Fantastic lecture, Serge.
Thank you.
One question which is almost, it is philosophical.
Yeah.
The laws of quantum physics predict the Big Bang.
Yeah.
So they were valid before the Big Bang?
That's again, what is the definition?
Some physicists talk like this. Yeah.
What is the definition of time? Was there a time before the Big Bang? This is a question I cannot answer. It's, there are some theories which say that we are only one universe among many.
Absolutely.
Because in our universe, what is fantastic is that the fundamental constants are tuned in the way which has made possible the emergence of all the elements,
Yes,
especially carbon and so on.
Hypothesis.
So this hypothesis says, okay, there are a lot of universes. We are in the one in which we are lucky, so we don't have to ask ourselves any more questions that someone who wins at the lottery. There is no explanation for that. I think I'm not quite satisfied by this vision, but why not?
Okay.
And of course, I did not say anything about life. I think you will talk a little bit more about life. Life is something which is different, which cannot be explained just by the laws of quantum physics, clearly.
Mm-hmm. Yeah. Yeah. Yeah.
Yes.
Thank you, Professor, for showing us the grand picture of quantum physics in the past century. So my question is, well, actually QED or quantum optics are rather abstract theory.
Yeah.
And even in experiment, it's very hard to take a very close look at one particular atom. So would you please do some predictions on the applications of those theory in the very soon future?
Yeah. No, first of all, what you said is true. These theories are very precise. QED can predict, for example, the magnetic moment of the electron with 10 significant digits, and it's verified at this level of precision. And the measurements are even more precise than that. Now, I've shown you that measurements have 18 digits, and no theory can compute with 18 digits. So the experiments are well ahead of theories. Now, what would be the use of all of this? There are many predictions. Of course, the one everybody talks about is a quantum computer. If you can control a large ensemble of atoms or quantum systems and avoid all kind of perturbation called decoherence, at least in principle, you should be able to build up computers which will have a fantastic power because they will compute in parallel over many quantum trajectories, and then by an interference effect give you a result that classical computer would be unable to give you. But this is an utopia for the time being because nobody knows how to control this at this level of precision. On the other hand, you can build already what is called quantum simulators. You can build from the bottom up small crystals made of a few tens or few hundreds of atoms and control exactly their position and the way they interact with each other. And as soon as you get more than 50 particles, no classical computer can solve Schrödinger's equation. So these simulators will give us a hint about maybe new state of matter that you can build, for instance, to get superconductivity at high temperature, or build new molecules which will have some interesting properties for curing some diseases. So this is called quantum simulation, and this is already happening. These quantum simulators with cold atoms or with ions in traps or with superconducting circuits are already existing, and this will work. Another domain is quantum communication. If you can send quantum particles and use entanglement, you can communicate at a distance without being any possibility of being spied upon. And this is working, and in particular in China, there have been a lot of development in quantum communication. And the last domain is quantum metrology. You can use the quantum properties to build probes which are much more sensitive than classical probes. I gave you only one example, which is the clocks. But it's not only clocks. You can use also quantum metrology to make extremely precise measurement of lenses, of electric and magnetic fields. And these probes are already being developed with various systems. So what will really happen, we don't know, but we have some indication of the direction in which this so-called second quantum revolution is leading us to.
Okay, due to the time limitation, we need to stop here. So thanks again, Mr. Haroche.